floor is for Howard Wiseman from Griffith University, who is going to present probably the most popular paper of the year on quantum foundations and related thoughts. And please, a reminder for those of you who just joined that if you want to ask questions, please alert me. You can send a question or just ask me that you want to ask a question, and then I will let you speak when it's time. Howard, please.
So can everybody see my screen?
Yes, we are fine.
Yes, excellent. Okay. So yes, thank you to the organizers for inviting me to talk here. And my topic is so quite closely related to what Ruth Kastner talked about in the previous talk, and I guess the theme of reversibility or irreversibility runs through all the talks so far, including this one. Anyway, as will become clear. So my title is Can a Qubit Be Your Friend? Why Experimental Metaphysics Needs a Quantum Computer. And so I'm in the Center for Quantum Dynamics at Griffith University here in Brisbane and the Gold Coast in Australia. And this work is funded by the Foundational Questions Institute and by the Center for Quantum Computation and Communication Technology. Okay, so this obviously is not, well, yes, is not just my work. So I will be, the basic theorem that I will be presenting and briefly experiment that I will be presenting today comes from this paper that Valeria mentioned, which was published just this year. And so it's mostly Griffith University authors, some of whom are in the audience, and also Yongcheng Liang in Taiwan, National Tsinghua University. But also I will be talking about material that goes beyond what is in this Nature Physics paper. And this is still in preparation work with one of the co-authors of that work, Eric Cavalcanti, and also with Eleanor Rieffel at NASA. And yeah, I put up a different picture to go with that one, and you will see how that's relevant as we go along. Okay, so motivation. So, so this is the structure. So I'm going to begin with an introduction, which is motivation and historical background, and then get on to the new theorem and the new experiment that I'll be talking about. And then in the third section, the sort of going beyond that, being more speculative and talking about future possibilities and implications for quantum interpretations. So yes, as I said, motivation to begin with. So the real motivation for this work is to find new customers for quantum computers. And we have identified this huge market of philosophers wanting to advance experimental metaphysics. Okay, maybe not such a huge market, but so this word is one that Ruth already introduced in her talk, but I guess assumed that everybody was familiar with. But for those who maybe are not, what do we mean by metaphysics? Well, this is just a dictionary definition, that it's the branch of philosophies which deals with the first principles of things. So in one might say the most important things that one could possibly think about. That's a particular point of view, of course. I'm not necessarily endorsing that, including abstract concepts such as being, knowing, identity, time, and space. Okay, so the real motivation for this work is that we are interested in these things. And so many physicists are interested in these things. Not all physicists, but that many are. Now, metaphysics in itself, as it says here, has a branch, is treated as a branch of philosophy. But when we talk about experimental metaphysics, then we are really talking about science, something that's not, well, it is philosophy, but it's also science. And this was a phrase introduced by a philosopher, Abner Shimony, in 1987 in this collection of papers here. philosophical consequences of quantum theory. And it's a phrase which has begun to have more usage again recently. And so, for instance, there was this 30-year anniversary conference in 2017 of this phrase, which took the title Experimental Metaphysics 30 years on. And I'd say so one of the presenters at that conference was Eric Cavalcanti, who was co-author on the work that I'm presenting here. Okay, so the idea of experimental metaphysics is that we can actually test in conjunction metaphysical assumptions, okay, which traditionally have been thought of as things that philosophers worry about, thought of by scientists at least, as things that philosophers write treatises about or whatever, but have no relevance to the real world. The point is that we can actually, by making conjunctions of various metaphysical assumptions, come up with things which can be tested experimentally. And this whole field started, as you can guess from the subtitle of this book, from Bell's theorem. So that's where I'm going to start in this historical review, is to just say a little bit about Bell's theorem. So Bell's theorem, of course, dating to 1964. This is the title. Here's a picture of Bell from slightly later. What does it say? Well, I think actually a quote from this paper explains things pretty clearly. He says, the statistical predictions of quantum mechanics, and I'm putting this in brown to distinguish it from the rest for reasons that will become obvious. The statistical predictions of quantum mechanics are incompatible with separable predetermination. Okay, what does that mean? He explains that is, in any theory in which parameters determine the results of individual measurements, so that's the predetermination part, there must be, well, the other part must be wrong, which he explains means that there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay, so as I said, this part in brown is separate because these things talking about predetermination and separability or something like that are really metaphysical assumptions, which we'll make more precise in a minute. Whereas this thing in brown is just something that experimentalists can test. Okay, they can go into the lab and see whether we actually get experiments which accord with the statistical predictions of quantum mechanics. So the point is that in Bell's theorem, it's not a, well, it's a theorem about quantum mechanics only insofar as it assumes that quantum mechanics gives the correct predictions for experiments. Okay. And so at least since 2015, arguably earlier, we don't even need to mention quantum mechanics at all when we talk about what Bell's theorem is about. So fundamentally now we can say Bell's theorem is not about, well, or at least to say the implications of Bell's theorems are not about quantum mechanics. The implications, because we now have experiments, the implications are purely metaphysical. Okay, and to be a bit more formal about it than Bell did, there are obviously many different ways of formalizing Bell's theorem in this way in terms of metaphysical assumptions, but these are the assumptions that I'm going to make for the purpose of this talk. Okay, we can say the Bell experiments rule out the conjunction of these three metaphysical assumptions. So the first one I'll call absoluteness of observation. Sorry. An observation is a real single event and not relative to anything or anyone. Now, Bell didn't mention this. This was completely implicit in his treatment. He just assumed, well, obviously that this is the case, okay? That when an observation happens. There's nothing more to be said about it. And that's essentially what this assumption means. Okay, second one, predetermination, which was an explicit assumption of Bell, predetermination of observable events. Surprisingly, to actually write that out formally, it's bit technical and yucky, which is what I intended to convey here. And I don't actually want to go through this definition because, as we'll see, this is what we're going to get rid of in the work going forwards. So if you have an intuitive idea about what predetermination means, then that's probably fine. For this purpose, it's basically, yeah, the idea that there's something in the past that is going to determine the observable events. Okay, and then finally, the critical assumption, third critical assumption, is one which we are going to call, I'm going to call in this talk, local action. And so just a caveat on that, this is not the same, not quite the same as locality. Not quite the same, well, definitely not the same as local causality, but it is the only other assumption which we need to derive Bell inequalities, which I'll talk about briefly. So local action is this assumption that any free choice made in a manner appropriate for a randomized experiment is, for the purpose of that experiment, correlated only with events in its future light cone. And yeah, if people really have urgent questions, technical questions, then I'm prepared to take them during the course, but broader questions obviously should be at the end. Okay. All right. So what are the implications of these metaphysical assumptions? So in a typical Bell scenario, we have two parties. So this is a space-time diagram, space horizontally, time vertically. I have Alice's lab over in this space and Bob's lab over in this space. And so Alice chooses some setting in a manner appropriate for a randomized experiment. Bob chooses some setting Y over here, Alice is X. And then at some short time later, Alice gets an outcome A and Bob gets an outcome B. Okay, so the absoluteness of outcomes just means that, you know, these events A and B do jointly exist. I can think of, you know, joint probability distributions for A and B. I can just treat them as variables in the normal way that I would expect to be able to. Okay, and then down in the past, we have a hypothetical hidden variables, as they're often called, things that, if we assume predetermination, are going to determine the outcomes A and B. Okay, so these formally we define them to exist on a space-like hypersurface, which is prior to these settings, and then everything goes from here. Okay, so the assumption of predetermination, what that says in a context like this is that the probability of getting outcome A, given all the things that could be relevant, so these hidden variables, these settings for X and Y, those probabilities are either 0 or 1. That's what it means. In other words, if I know all of these things, I know exactly what outcome I will get. Okay, there's either I will definitely will get this outcome or will definitely not get this outcome for a given A. That's what this equation means, and likewise for B. And I could have considered obviously a joint outcome for A and B, and it would similarly, you know, either it happens or it doesn't happen if I know all those variables. This is what predetermination means. Local action now, remember that means that these freely chosen settings are uncorrelated with any variables except those in the future light cone. What that means is that I can say more about this probability of A given lambda X and Y. It's that it actually cannot depend on Y because A is not in the future light cone of Y. So these diagonal lines are meant to represent light signals, potential light signals, so they define the light cones. And Y over here is, we say, space-like separated to the outcome A over here, and so that cannot depend on that. And similarly, the probability of B cannot actually depend on the setting X, but it can depend on everything else. And with this definition for local action, we also can say that the probability for lambda, for these hypothetical variables that may exist here, cannot depend on X and Y because they are not in the future light cone of X and Y. Okay, so I take these equations, all of these equations, do some manipulating with them, and what they imply is some constraints on the joint probability distribution for A and B given X and Y, which, as I said, is that, yeah, we can consider that because from assuming the absoluteness of observed events. They imply constraints on these, which conventionally we call Bell inequalities. Okay, they're just they're just statements about limits on the possible values that this probability can have. And the point is that these probabilities are the ones which experimentalists can measure. Experimentalists cannot measure any of these probabilities because these lambdas are, by assumption, hidden variables. Okay, they're not macroscopic. I mean, that might be, but we're going to allow them to be microscopic and say that the experiment consists only of choosing settings and seeing outcomes. And so the experiment can measure these probabilities, and we get, as I said, constraints on those, and we can violate those constraints. In fact, we have violated those constraints, and that's what happens when we do a Bell experiment. Okay, which means when we do that violations, that just briefly going back, that means that at least one of these metaphysical assumptions has to be wrong. Okay, that's the significance of Bell experiments. And again, to emphasize, no mention of quantum mechanics anywhere on this page. Right. Okay. So in contrast now, I'm going to move to another historically relevant and interesting paper, which is this one by Eugene Wigner. So around about the same time as Bell, just slightly earlier in 1961, he wrote a book chapter with the titled Remarks on the Mind-Body Question. And so this is not, unlike Bell, this is not a theorem. It's, as I call it here, it's musings, if you like. And also, unlike Bell, this is very much in the context of quantum mechanics. Okay, this is just talking about quantum mechanics as a theory and what it says and what it doesn't say, etc. Okay, so I think it's so Ruth also mentioned obviously this Wigner's paper, but I think it's useful again to let Wigner actually talk to himself about what he was saying. So he says, it is natural to ask about the situation if one does not make an observation of a microscopic system, he means, oneself, but let someone else carry it out. What is the wave function if my friend looked at the quantum object? The answer is that one could only attribute a wave function to the joint system of friend plus object, which he writes here. So this is this superposition, or indeed an entangled state between the friend state and the microscopic state of the system. And he said that this form, this superposition, follows from the linearity of Schrodinger's equation. And then he says immediately, this appears absurd because it implies that my friend was in a state of suspended animation before he answered my question about what he saw. In other words, before, so he's now going to let the friend make the observation and then ask the friend, what did you see? And he's saying before the friend answered, the friend must have been in a superposition like this. So like Schrodinger, as Ruth talked about, Wigner was not proposing his friend scenario as a way of saying, oh, look, quantum mechanics predicts that friends are exist in a superposition. Isn't that interesting? No, he was saying quantum mechanics predicts that friends must be in this superposition. Isn't that absurd? Okay, isn't that in fact wrong, as he went on to say? He says, it follows that Schrodinger's equation cannot be linear if it is accepted that my friend has the same types of impressions and sensations as I. Okay, and he goes on and says some other interesting things, but that's the gist of it. Okay, so there we have two completely different types of things. One, a theorem about experimental metaphysics, another one, a musing about quantum mechanics itself and observers, etc. But what's happened in recent years is that people have had the idea of putting this together. And I don't want to say exactly who had the idea first, but certainly This work by Czesław Brukner, I think, was done independently of the work by Frachiger and Renner, and this one is more relevant to what I'm going to tell you about. So this is the one that I will, talk about. Okay, so Czesław, yes, published in 2018, this a no-go theorem for observer-independent facts. Okay, so yes, so the idea was to incorporate Wigner's friends into a Bell experiment, essentially. And the motivation for that was to get rid of the predetermination metaphysical assumption, the one that I did in this sickly green color to say that it's really ugly and it's the one that most people say with Bell's theorem. Well, obviously that's the one that we should get rid of. So this is exactly the idea of getting rid of that, but replacing it with something else by basically making the friends' observations play the role of the hidden variables. And I'll show you pictures in a minute, which will explain how this works. So in this way of thinking, because of course quantum mechanics, quantum experiments have come along enormously in the 60 years, almost since Wigner wrote, now rather than thinking that saying that friends could exist in a superposition is obviously absurd, we tend to believe that, well, until proven wrong, we'll assume that quantum mechanics does actually apply at all scales. Okay, so that friends maybe can be in superposition, okay? And therefore it is interesting to think about deriving consequences from that assumption. That's not to say that that assumption is necessarily right, but let's just make it and see where we get. Now, so this was a very important paper for us. However, it had a slight problem, is that the way Brukner had this intuition of replacing predetermination by the reality of the observations of friends. But unfortunately, the way he did it, he actually formalized his assumptions in a way that made them at least as strong as the assumptions that Bell had already made for his theorem. So in other words, you don't actually get anything different or new compared to Bell's theorem from using the formulation that Brukner did. But that's not the end of the story, because what we did in our work was to realize that one could actually formalize these intuitions of Brukner in a way that was strictly weaker than the assumptions used by Bell's theorem, and thereby derive a new theorem of experimental metaphysics, which is what I'm going to tell you about. So the Griffith Theorem, if we call it that, as published in this paper here, is as follows. So essentially we take, if you remember the three assumptions which I listed for Bell's theorem before, in terms of the metaphysical assumptions, we literally just drop one of those assumptions. So we simply drop the assumption of predetermination. So the metaphysical assumptions are just one that we had before, absoluteness of observation. An observation is a real single event and not relative to anything or anyone. And local action, okay, any free choice is correlated only with events in its future outcome. However, right, in terms of assumptions which are not metaphysical, right, assumptions about what would be necessary to do the experiment, Bell only had to assume that, well, quantum mechanics basically gives the right answer for measurements on entangled states over large distances, okay, which was not at all obvious when he proved his theorem, but which we now know is that it is. So similarly, we have to make an assumption about what could be observed, which is not obvious, but which may be true, okay? It requires experiments. So I'm cheekily calling this assumption superpowers. We don't call it that in the paper, but this is because it's basically the assumption about what a super observer can do. So in these types of experiments, Wigner is sometimes called the super observer. And so I'm going to say that Wigner has superpowers. Wigner can perform arbitrary quantum operations on an observer, in other words, his friend, and if necessary, the environment of the observer. Okay, so yes, that's what I said. So this, yes, stress again, yes, that this is not a metaphysical assumption. We can decide this experimentally for a given Wigner and a given friend. Okay, so only two metaphysical assumptions as it's formulated. Okay, so how does this work? So let's assume that we have two friends. there, which we'll call Charlie and Debbie. And they share an entangled state here. So that's what this cartoon is meant to represent. Now, let me just concentrate, and they're going to make measurements on those. Okay, so they make measurements and get some results. They're inside boxes, obviously. I'm now going to just concentrate on one side and introduce a Wigner, a super observer, an external. Now, if Alice has a measurement choice. Okay, this is critical. Just as in Bell experiments, she has a measurement choice. If she makes choice 1, then what she does is basically open the box and ask Charlie what he saw. Okay, and then she writes that down as her result A. Okay. On the other hand, right, if she chooses a different setting, so x not equal to 1, maybe x equals 2 or something like that, then what she does is not open the box, but instead press a button which reverses time inside the box. So reverses time means that Charlie has no longer made his measurement. Okay, the memory, Charlie's memory is erased in a completely reversible way, that the particle becomes unentangled with Charlie. And then Alice can simply throw Charlie away and make her own measurement on this particle that remains and get an outcome from that, which again she writes down as her result A. Yeah, okay. So on the other side, Bob is doing the same with Debbie. And then we can ask, okay, what implications follow from this? Well, so the assumption of absoluteness of observed events, in this case, we have to remember that there's not just the observed events A and B for Alice and Bob. Charlie and Debbie are also assumed they actually made a measurement. Okay, whether or not it gets reversed later is irrelevant. They made a measurement, got an outcome, and absoluteness of observed events means that these variables C and D really exist. They exist jointly with A and B because that's what absoluteness of observed events means. Okay. So I can consider a joint distribution over all of those, A, B, C, D. Okay. And that's a positive probability distribution. And so I can say, well, that's a constraint, right? And it's just the laws of probability says that the observable by the super observers, the observable probabilities, P of A, B given X, Y, there is absolutely no doubt that these are observable probabilities, right? Is given simply by marginalizing over the variables C and D. Okay, and we also know that if Alice chooses x equals 1, then she just writes down whatever Charlie saw, and if Bob chooses y equals 1, he writes down whatever Debbie saw. Okay, so we get that, and then we have local action, which are basically the same as before, with the hidden variables being replaced by C and D. Okay. So I'm going to use the phrase local friendliness. This is what we did in the paper for the conjunction of these metaphysical assumptions here. And the point is that local friendliness, it's just a cute name, okay? It's just absoluteness and local action. Those things together, again, imply, do I write it there? Yes, okay. They imply constraints on these observable probabilities P of A, B given X, Y, okay? And now this is where superpowers come in. If the appropriate superpowers exist, okay, and they don't even have to be perfect. We don't actually have to assume that quantum mechanics is 100% completely, you know, applies to the whole universe or anything like that. We just have to say that Alice, some reasonably good approximation, can do the things that do the reversal operation, for example, that I talked about, such that if Alice and Bob undo Charlie's and Debbie's measurements, the probabilities they observe in those instances is approximately the same as what they would have observed if there was just no Charlie and Debbie at all, and they had just directly measured the entangled particles that I talked about again. Okay, so if this approximate inequality holds, then these probabilities can violate inequalities or constraints that are derived from the assumption of local friendliness. Okay, so in other words, what we have here is a new theorem of experimental metaphysics in which the metaphysical assumptions are strictly weaker than those of Bell's. We've literally just taken one of Bell's assumptions and thrown it away. Okay. Okay, so as I said, this this paper also had an experiment. Now there are a lot of details that I could go into about what we measured in the experiment and why we measured it and what it showed and how we designed it and things like that. And this is just to show you that these slides exist, so that if you're interested in any of these details, feel free to ask me and I can go to them at the end. But I thought in the interest of time, I'll skip over these and actually just talk about conceptually, I think what's the most interesting thing, which is what the experiment looks like. Okay, so here's the experiment. So we have an entangled qubit, two entangled qubits, which are the polarization states of photons. Okay, so the polarization of this photon is entangled with the polarization of this photon. They go, so these boxes here are Alice's and, Charlie's and Debbie's labs, if you like. So this is very important. So what are Charlie and Debbie? Okay, Charlie and Debbie are also just a single qubit. Okay, so Charlie is the single qubit, which is the path of the photon. Okay, so the entangled qubits were taken to be the polarization of the photon. The other qubit, which is the friend, is the path of the photon. And so the measurement, okay, by Charlie of the polarization of the photon is simply creating a perfect correlation or near perfect correlation between the path of the photon and the polarization of the photon, which is something which can be done with this polarizing beam displacer here. Okay, now if Alice chooses x equals 1 and she just wants to know what is the polarization of the photon, she just asks Charlie what he saw, which, to put it in physical terms, means she just reflects the photon here. And so if Charlie is in this state, in this path, then Alice will get a click in this detector. And if Charlie is in this state, in other words, the photon is in this path, then Alice will get a click at this detector. Okay, and that's how Alice asks Charlie what he saw. Right. If Alice wants to make a different measurement on the polarization of the particle, then she simply reverses this by using another, various optical elements, including another polarization beam displacer, which simply erases the information, so that what comes out here is that there is only one path for the photon. So Charlie, if you like, is just in the same state that he started, right? Not correlated at all with the polarization. And Alice then just makes her own measurement of polarization in any way she wants using this polarizing beam splitter here. And she can choose the setting for that as she sees fit. And then on the other side, we have Bob and Debbie doing the same things. And in the end, what we look at is correlations between so the outcomes, Alice's outcomes, which are depending on what she chooses, the clicks on these detectors, and similarly for Bob. So we look at, going back to, we look at these probabilities and look for violations of the local friendliness inequalities that we derive. Okay, so what did we see? We saw an experimental violation of a local friendliness inequality by more than 17 standard deviations. So we can say that we have violated local friendliness, or can we? Okay, as I said, each friend was only a single qubit, this photon path. So that in the total experiment, there are only 2 photons, but there are 4 qubits, okay? 2 polarization qubits, 2 path qubits. And that's how we were able to do the experiment, even though we don't actually have superpowers. I mean, obviously the experimentalists are very good at their work, but they don't actually have superpowers. And so that made it a feasible experiment. But this opens the question, which is the title of my talk: can a qubit be your friend or be a friend? Okay, so different people have different views on this. My personal view, and it more or less matches what we say in the paper, is no. Obviously, a qubit is not a real friend, and in the paper we call this a microscopic proof of principle version of the experiment, not a real local friendliness experiment. Okay, so that just to to be clear about that. But the point is that this doesn't mean that the whole thing is a toy waste of time or whatever, because this is just the first step on the way to a real experiment. So what would make a real experiment? What would make a physical system, a friend, a real friend? Well, there are different attitudes you could take to that. As I said, some people think that even a single qubit is already a friend. But leaving that aside, what about just making the quantum system much larger or more complex? Well, I think that's an interesting direction to go, but there are numerous different criteria for, size and complexity, and no really agreed thresholds about, when you go above this level, then it's a macroscopic system or whatever. Okay, nobody agrees about that. All right, so what about this idea for what makes something a real observation? An irreversible active amplification, as Bohr said, according to Wheeler at least. Well, yes, that undeniably, if you have that, then you have a real observation. But if we go with that, then it would just make that impossible to do an experiment like this, because the whole essence of the experiment is the assumption that we can undo the measurements by the friends, that we have these superpowers which lets us do that. So if it's irreversible by definition, if it has to be irreversible by definition, then we're just never going to see a violation, and that doesn't seem to be a very interesting direction to go. So then if we go back to Wigner, we could say, what did he mean by friend? He meant a sentient being with the same types of impressions and sensations as I. And you might say, well, that's obviously out of the question, but I will disagree and say that that is actually the best feasible option. You're going to say, well, but how could we possibly do that? How could we realize a sentient observer and be able to unitarily reverse that being, that the physical state of that being? And I will say, well, it will have to be an artificial intelligence realized on a truly enormous fault-tolerant quantum computer. Okay, so this is where we get back to why experimental metaphysicists want a quantum computer. Okay, so how is this going to work? So this is the third section. So very similar to before, it actually turns out that we don't need two friends. In fact, we can make do with just one friend. So we don't have to build two enormously large fault-tolerant quantum computers. I'll just draw one. So we call him Charlie. So Charlie is here having whatever thoughts Charlie might happen to be having as an artificial intelligence. We don't know what that is. We're not going to pry into his private thoughts or anything like that. We don't need to know what his state is. That would be unethical. But we're going to let him make a measurement. And so here comes this qubit. Charlie is just himself an enormous collection of qubits. This qubit joins in the fun and, gets processed along with everything else that is Charlie. And Charlie then sees some particular result. Okay, this is what it means if he's actually an artificial intelligence. Presumably, if it's encoded in the right way, we can make it a whole bunch of qubits if we want. Whatever, there's going to be some way to ensure that Charlie actually observes some outcome from getting this system. This is not making any physical assumptions. We're just assuming that that's what, if Charlie's an observer, then surely Charlie will be able to, the thoughts of Charlie will represent an outcome. Okay, so then if Alice chooses x equals 1, she just wants to know what Charlie saw. She just asks him, and Charlie's screen gives some output, which Alice observes. Again, if Alice wants to do some other measurement, she simply runs the clock in reverse. She reverses the operation of the quantum computer that is Charlie, so that Charlie ends up being, again, unentangled with this qubit here. Heartlessly, Alice again just throws Charlie away, and keeps the qubit and makes whatever measurement she wants on that to get her outcome. Okay, and essentially we get then the same, yes, by those assumptions, we get the inequalities which can be violated. Okay, so how difficult would this experiment be? Extraordinarily difficult. Okay, so people worry about how difficult it would be to make a quantum computer which is to do some useful calculation in biology or factor some large numbers or something. I mean, this is obviously just on a whole level, many levels above that. Okay, so probably Yeah, depending on, it's not really clear, depending on what you think is necessary to simulate a sentient being, it could be more or less difficult. If you think that it's actually necessary to simulate things at the level of neurons or you know, even smaller, then we're talking some absolutely ridiculously large number of logical qubits. But then things might not be that bad. Maybe we just have to have some sort of artificial intelligence, human level artificial intelligence algorithm, which might only require trillions of logical qubits or something like that. So it's going to be big, whichever way, but not actually inconceivable, I would argue. Okay, and so then this Charlie is this huge computer. We have to treat him like a friend. We have two-way communication with Charlie until we're convinced that he is actually a human level artificial intelligence. And then once we are convinced, then we can begin the experiment, which involves this, you know, reversal bit. So during the experiment, Charlie would have to be completely isolated while he makes his measurement, no longer actually talking to the outside world. And so that if we needed to, we could reverse his evolution and then get the qubit back. Okay, so as well as these practical questions about building the quantum computer big enough to run Charlie, there are also ethical questions about would Charlie want to participate in such an experiment, given that, you know, we have to tell him that what's going to happen is, you know, we're going to reverse your time, and whatever you experience, that's just going to be undone. He might not like that. But even if he did like that, would we actually get ethical approval to perform such an experiment? I think these are going to be difficult questions with artificial intelligence in general, not just to do with quantum artificial intelligence. So hopefully they'll be sorted out before we have to worry about actually performing an experiment. But let's say that we imagine that we actually could do that experiment. Well, first of all, okay, sorry, before doing that, the point about this whole scenario is that I want to talk about a real experiment without just, you know, throwing in superpowers, okay, which is this totally implausible idea. The idea is to say, here's a very difficult but conceivable experiment which we could do. And what are, okay, and I also want to reformulate the metaphysical assumptions. So I want to reformulate them as things that break them down basically into things that are each individually look really quite hard to give up. Okay, so all of these look like very plausible things that we would like to hold on to in our picture of, you know, the most fundamental nature of the universe. So they are, to read them out. So this is the unpublished work. Okay, so I won't say that this is necessarily the absolute final formulation that we will use, but this is where we are so far. Physicalism. A thought has an associated physical process in the brain or other information processing unit, obviously, as necessary, as appropriate. 2, ego absoluteness. My thoughts, so ego meaning as in me, right? My thoughts are absolutely real if I would be able, if asked, to communicate them to another party. So this is where the absoluteness comes in, but I'm now pinning it on just me for the moment, because how we generalize this is to now have a, or make this apply more generally, is to have another assumption, which I'm going to explicitly call friendliness here. If I find other parties to be cognitively equal to me, then their thoughts have the same ontological status as mine. Okay, so that's not committing to what that ontological status is, but obviously if I also assume ego absoluteness, then that means that I'm also assuming that these other parties have thoughts that are absolutely real. And if I assume physicalism, that means that there are actually events in the physical world that are absolutely real. Okay. Now, as I said, without superpowers, we want to replace that by actually conceivable technological assumptions. First, that human level artificial intelligence is possible, which I'm using. And second, that universal quantum computing can be done at a very large scale and reasonably fast. Okay, emphasizing the very large scale. And then finally, the other metaphysical assumption is the one that's been coming along for the ride the whole time in all of these: local action. And in this case, we only actually need to worry about human free choice, but whatever, any free choice is correlated only with events in its future lifetime. Okay, so again, these are the metaphysical ones. Okay, so yeah, what if we could actually do this experiment then? Or not even, let's say, not even if we could do this experiment. This is a conceivable experiment. What are the implications of that fact, okay, that these assumptions, right, for metaphysical to empirical, what are the implications of the fact that these 6 assumptions lead to a contradiction? Well, that means at least one of them must be wrong. But what one you think is wrong is very much going to depend on what your interpretation of quantum mechanics is. And I guess, yeah, to leave time for questions, I won't spend too long on this slide, but just to point out that we can identify interpretations or modifications of quantum mechanics and sort of classes of them, such that for each of those 6 assumptions, that interpretation says this is the one to give up. Okay, so at one end, so Wigner's original idea, then that consciousness causes collapse, would very interestingly, if Wigner is right about that, then it would not be possible to do universal quantum computing. Because when we tried to put a universal quantum computer into, which is running a human level artificial intelligence algorithm, trying to put that into superposition, it would just collapse into one of those 2 possibilities. And yeah, so that's a very interesting possibility, right, which we can't rule out until we've actually done the experiment. There are, yes, there are the ideas of Penrose, which I think imply that human level artificial intelligence is not in itself possible. There are spontaneous collapse models, which imply that not everything that appears to be intelligent is actually having real thoughts. There are no necessarily real events associated with that. So this, interestingly, actually says that we have to reject the assumption of friendliness, however unfriendly it seems to do that. There are a whole heap of interpretations which on the face of it don't seem very similar, like cubism and Everett's many worlds, which in this schema actually deny the ego absolutism. There are some weird ones which deny physicalism, and there's the whole class of hidden variable theories which just say, in what I think is essentially the most straightforward way out of the dilemma, just to say that local action is not true. Okay, you have some sort of non-locality in the theory. I'm not saying that that's the right answer. I'm just saying that that's the sort of easiest one to understand of all of these assumptions. Okay, and then what I would say is that probably most physicists, if you ask them individually about each one of these assumptions and defined it for them, they would probably say, oh yeah, I think that's true, I think that's true, I think et cetera, right? And so what we would end up with then is that these physicists who don't actually have an interpretation of quantum mechanics, who haven't really thought things through, that we can just say, well, there's a problem there, right? You actually have to think things through and have a real interpretation in order to be able to deal with this theorem, which I think is more yeah, not the case with a lot of other theorems which have been proposed. Okay, so to finish, so the whole idea of experimental metaphysics is that metaphysical assumptions which are not testable individually can have falsifiable empirical consequences in conjunction. Okay, and in the case of Bell, they are indeed falsified empirical consequences. So what we have shown in this work is that with continued advances in artificial intelligence and quantum computing, that there will be a new frontier in experimental physics opening up. And specifically, what we could do with this technology is to rule out, potentially, depending on how the experiment came out, the conjunction of the metaphysical assumptions of physicalism, ego, a thought has an associated physical process, ego absolutism, my thoughts are absolutely real, friendliness, I'll give other people treat other people the same as myself, and local action or other parties the same as myself, and local action, any free choice can be assumed to be uncorrelated with events outside its future lifetime. And as I said, we performed a proof of concept experiment in this area, but the real experiment is a long way in the future, in my opinion. Okay, thank you.
Okay, thank you, Howard. I have two questions in the first one is by John Koo, who was an undergraduate student. John, would you want to ask your question?
Hi, thank you, Professor, for the talk. It's very interesting. Okay, so my question is basically this: if a sufficiently complex quantum computer would count as sentient, then there's nothing.
Do you want to put your video on if you can?
Okay, sure.
Or if you don't have video, then that's fine.
Yeah, hi. Okay, so if a sufficiently complex quantum computer is counts as sentient, then there's nothing qualitatively special about sentience that would differentiate a AI running on a quantum computer from a qubit, right?
Well, I mean, I think the whole well, it's not just the idea that you build a large quantum computer and it will be sentient. The idea is you have an artificial intelligence program which you would need a very large quantum computer to run on. Okay, and once you run it, then you are able to interact with that computer and decide for yourself whether you think that it's sentient or not.
Right. So it's the algorithm that makes the sentience. Because what I'm curious about is what is sentience in this framework.
Yeah. Okay. So nobody knows what is sentience, right? So essentially, the way that I've approached the problem here is just to the sort of traditional Turing approach, which is just that if I interact in an open-ended way with another party and they seem to be sentient to me, then I will give them the benefit of the doubt and say that they are sentient.
But that seems to be a very odd property to predicate the ability to collapse wave functions on, right?
It's not one that is commonly considered in physics, but it is exactly the one that Wigner considered.
Right.
I mean, Wigner was saying exactly that Schrodinger's equation must be wrong because there are sentient physical systems, and I don't believe that sentient physical systems can be in superpositions.
Right. I guess my confusion is just that I don't think Wigner was thinking specifically of this particular definition, which seems to be very odd to assign such metaphysical significance to.
Well, he didn't really go into great detail, but he called his friend a friend, and that's basically all he said about him. Okay, he considered a friend with the same type of whatever the quote was, the same kind of same types of impressions and sensations as I. Now, of course, there's no way we can know what the impressions or sensations of another being are. The only thing we can do is to interact with them and eventually maybe become convinced that, well, I don't have any good reason not to think that they have impressions and sensations the same as I do.
Okay, I see. All right, that makes it a bit clearer. But I think this is still a very contentious area. I mean, there's all kinds of philosophical problems like the Chinese room and the issue of qualia and stuff like that.
Yeah, indeed, yes. And no, I mean, the formulation here was chosen specifically to avoid those sort of philosophical problems. It's really to make I mean, I think the nice thing about this formulation is that it avoids it, but it has this explicit assumption of friendliness, okay, which you could reject.
Okay, I see.
Do you mind if I just add something here, Howard?
I guess it's up to Valerio how many questions are in the waiting.
There was a question by Rahul. I don't know who is speaking now. Or Eric was intervening.
I just wanted to make a comment.
Make a quick comment in reply to his question.
Okay, please make it quick because we have another question coming up.
Sure. The comment is just that it's not an assumption that an intelligent agent collapses the wave function. It is just the assumption that if you interact with an agent and you find it to be intelligent, then it has the same status as you have ontologically. Its thoughts have the same status as your.
Yeah, that's very good. Thank you, Eric, for making that point. Is that again? Yeah, I want to emphasize that apart from this technological assumption about universal quantum computing, these assumptions have nothing to do with quantum mechanics. Okay, there are no assumptions here which say anything about this collapses a wave function or this doesn't collapse a wave function or anything like that. They're purely metaphysical assumptions.
Right. Okay. Okay. That clarifies a lot. Thank you.
Okay. Yeah.
Howard and also Eric for the clarification. Rahul, do you want to ask your question? Probably would be our last question unless someone urgently pings me. Rahul, please go ahead.
Okay, thanks.
Again, could you show your video? Just
oh yeah. Am I visible?
Well,
yep, half of you.
Okay.
Your camera. Yeah, now you're visible. Yes.
Okay. So yeah. So the like in our understanding of this Fauci-Renner proposal, right? I mean, one issue that we find is that, I mean, they seem to be making these implications, right, which we have in classical probability, that, A implies B and B implies C, then A implies C, okay? Now, these implications for quantum events ABC are not necessarily true because events change the state, the underlying state is changed, right?
Okay, so maybe so you're making a comment about the Frege-Renner theorem. So I would say, like, I haven't talked about that at all in this talk. Okay.
No. So
and maybe just to make the comment again that you brought up quantum states, and right. There is nothing in these metaphysical assumptions about quantum states.
No, I agree, but I'm just saying that in this the FR proposal, I mean, the one issue that we found was that they were implicitly doing these implications that A implies B and B implies C, so A implies C, which are not necessarily true for quantum events. So I'm just wondering if in the current setup, anywhere such implications are being made for quantum events. That's
well, I guess, as I say, we don't have the word quantum anywhere in these metaphysical assumptions. So what is a quantum event? Is my observation a quantum event? If I observe something, is that a quantum event?
No, so let's leave out whether for quantum events, but for events in your experiment, are you doing these conclusions that A implies B and B implies C, so A implies C?
We assume that events, well, we don't do it by implications, but we assume that going back to the simpler assumption, we assume that these events that they are absolute. So in that sense, yes, I mean, any classical, they can be manipulated. They're just variables that can be manipulated according to classical probability theory, if you like.
Yeah, exactly. So that was an issue with FR as well. I mean, that assumption.
Well, I don't know. I wouldn't say it's an issue. I mean, I think they're also pretty specific about what their assumptions are. I don't think there's any flaw of that nature in their assumptions. It's just that you could question, I can't remember exactly what their assumptions are, but you could question whatever assumption it is that lets them do that. And in our theorem, you could question this assumption and just say, when it comes to quantum observers, at least, you just don't believe in this assumption. So it's not that there's anything wrong in the theorems. It's just saying, okay, this is the assumption that I don't believe.
This is an assumption that is being made, which for the physical theory may or may not hold. Yeah.
Well, okay, it's a metaphysical assumption. That's the point. It's not really to do with the physical theory at all. So we cannot say, it is just not possible to say that one is correct or incorrect. Okay, you can talk to me about quantum mechanics as long as you like. That doesn't prove that this is correct or incorrect. Okay, because this is a theorem which is about a metaphysical, experimental metaphysics, which means we just make metaphysical assumptions and we see what the consequences of those are. Now, one in itself has no consequences. It is absolutely impossible to say anything. You can say anything about, oh, but quantum mechanics experiments reveals this, blah, blah, blah. No, Quantum mechanics experiments can't say anything about whether observations are absolute or not. So it is, so if you reject it, that's just making a metaphysical choice. It's not something you can say on the basis of physics.
Yes, yes, true.
Okay,
definitely.
Okay. I mean, that said, of course, being guided in your metaphysics by, you know, your physical theory as you understand it is a perfectly reasonable thing to do. So I'm not saying, yeah, that's unreasonable, but yes, just to be clear that that's what it means. Yeah.
Yeah. And I mean, even for just simply plain and simple Bell experiments, right? I mean, the whatever model that is going to justify, you know, Bell observations will probably have to reject these implications.
Well, we have to reject again one of these
yeah. So
three
I
assumptions,
mean,
for
yeah.
example.
Okay, thanks.
Yeah, you're welcome.
So thank you very much for these. I thank all the speakers for all these talks, and also the participants for their intervention or their attention to their talks. Now we are going to make a break. You can, of course, leave the Zoom session and come back at 2:30 for the next two talks. The chairperson will be Quek. And so again, I thank you for your attention, and see you later for the second part of this seminar. Goodbye.